Hi. In this video, we are going to look at a standard technique where we use the triangle inequality to bound the roots of a polynomial. So basically, let's begin by analyzing this. Let R be a root of the polynomial p of x, which is given by ad x power d plus so on till a naught. What we do is we choose one term in the equality p of r is equal to 0. P of r is equal to 0. And, and we can think of it as a large term. Think of it as large in some sense. So what I mean is that we will isolate that term on one side of the equality. For example, if we pick the term AD R bar D as the large term, we will write AD R bar D is equal to minus of A D minus 1 R bar D minus 1 and so on till minus A naught, right? So basically we have used P of R is equal to 0 and we are picking one term. We are thinking that maybe this is the large term. We are keeping it on one side and writing the other terms on the other side. Now take modulus on both sides. We'll get AD R bar D is equal to modulus of A D minus 1 R bar D minus 1 plus all the terms till A naught. The minus sign is gone because of the modulus. And now we can use triangle inequality on the right hand side. We can say this is less than equal to mod of AD minus 1 mod of R bar D minus 1 plus terms like this plus mod of A naught, right? So we have used triangle inequality here. And then in the question, there will be some information that will be given to you, which will help you draw a conclusion from this step. So for example, if we assume in the question, suppose it was given if mod of R is greater than equal to 1, then let's see what comes from there. So we already have the inequality mod of AD R bar D is less than equal to mod of AD minus 1 R bar D minus 1 plus so on till plus A naught mod. And now if I assume mod of R is greater than 1, then what I can say is, here I will isolate mod of R here by dividing by, so first I'll take mod of AD on the other side. I'll get mod of R bar D is less than equal to mod of AD minus 1 by mod of AD, mod of R D minus 1 plus terms like this plus mod of A naught by mod of AD. And then I will divide by mod of R bar D minus 1. And I will get mod of R is less than equal to by mod of AD. And when I divide by mod of R by D minus 1 on both sides, this term is getting cancelled. And you have the next term would have been AD minus 2 by mod of AD, 1 by mod of R. And similarly, it will be increasing powers of mod of R in the denominator. The last term would have been something like this. 1 by mod of R bar D minus 1, right? This is what we are getting. Now we will use the fact that mod of R is greater than equal to 1. So this term is going to be less than equal to, if I replace every R with 1, right? So mod of R is greater than equal to 1. So this is actually smaller. So this is smaller than mod of AD minus 1 by mod of AD plus mod of AD minus 2 by mod of AD and so on till the end, till the last term, mod of A naught by mod of AD, right? Because mod r is greater than equal to 1, we are getting this inequality from here to here because we have replaced all the mod r's with 1, right? So now we are getting basically mod r is less than equal to mod of ad minus 1 plus mod of ad minus 2 till plus mod of a naught by mod of ad, right? So basically we have gotten this and we also knew this, we have used this also. So what we have found is that any root r of p of x has mod r is less than equal to the maximum of 1 and mod of ad minus 1 plus mod of ad minus 2 till mod of a naught by mod of ad. So whichever one is bigger, if this quantity is bigger than 1, we have mod r is less than the maximum. Mod r is less than this. And if 1 is bigger than this quantity, so we have mod r is greater than equal to 1 already, right? So we get this condition again, right? So basically what we will see is applications of this principle in different problems. So let's use it in a couple of questions to just understand the idea. So this is the first one. Find all complex numbers z satisfying simultaneously the equations z bar 2015 plus z bar 2014 plus mod z equals 3, and the second equation is 3z bar 2015 minus mod z bar 2014 minus z equals 1. We want complex numbers that satisfy both these equations simultaneously, right? Now, looking at the first equation, we can say that 3 is equal to, taking modulus on both sides, 3 is equal to mod of this, right? And obviously that we can apply triangles inequality here. We will say 3 is less than equal to mod of z power 2015 plus mod of z power 2014 plus mod of z. So we are getting this result. So this result implies that mod of z is greater than equal to 1. Why? Because if mod of z is less than 1, then all the terms are less than 1 here. And the whole thing will be less than 3. So 3 cannot be less than or equal to 3. Right? So this automatically implies that mod z is greater than 1. Now let's look at the second equation. We have 3z power 2015 is equal to mod z power 2014 plus z plus 1. And again we take modulus on both sides. 3 mod z power 2015 is equal to mod of mod z power 2014 plus z plus 1. And again we apply triangles inequality. We get less than equal to mod z power 2014 plus mod z plus 1. Right? Now if mod z is greater than 1, then what we get is, clearly we know that mod z power 2015 is greater than mod z power 2014, and we know that mod z power 2015 is also greater than mod z, and we also know mod z power 2015 is greater than 1, right? think about it. On the left hand side, I have 3 times mod z per 2015. And we know if mod z is greater than 1, this inequality is true. This is also true. This is also true. So the sum of these 3 times mod z per 2015 will be greater than this plus this plus this, which is actually the left hand side here. But apparently here they are saying it is less than equal to. But that is a contradiction. It cannot be greater than and less than equal to. The only option is that it is equal to 1. Both are equal to each other, right? So both sides have to be equal to each other, and we have the equality case of triangle inequality. And obviously mod z cannot be greater than 1. Mod z must be equal to 1, right? Mod z must be equal to 1, and in the equality case of the triangle inequality, I know that the ratio of the terms is a real number, right? So we have seen that before in the previous video, that if mod of a plus b plus c is equal to mod a plus mod b plus mod c, then a by b is positive real. And this is also true for b by c and c by a, right? So here we can say that z bar 2015, or even you can just work with z bar 2014 by z, that must be purely real, which means z is purely real. Z is purely real and mod z is 1. So therefore the only solution for this is the complex number z is equal to 1, which is actually a real number. This is the only solution. How did we arrive at this? We looked at the first one, we applied triangle inequality, we got mod z is greater than equal to 1. And then we looked at the second one, applied triangle inequality again, and in the case that mod z is greater than 1, we are getting a contradiction, we are getting an equality case, right? So that means mod z must be equal to 1. Mod z is equal to 1, the number 1 is the solution for this. And in the equality case, the complex number becomes real. We have seen that before in the previous video. So you should refer to that if you are slightly confused about that. Let's look at another problem. This is question 2. Let ABC be complex numbers such that all the roots of x cube plus ax square plus bx plus c equals 0 have modulus 1. Prove that all the roots of x cube plus mod a x square plus mod bx plus mod c equals 0 also have modulus 1. This is the question. So we are given the idea that the first equation has all roots having modulus 1. We have to prove that the second equation also has all roots having modulus, right? So let's see how we go about this one. So let's start with the first equation and say z1, z2, z3 are roots of x cube plus ax square plus bx plus c equals 0. And we will say let r1, r2, r3 be the roots of the second equation. Roots of x cube plus mod a x square plus mod bx plus mod c equals 0. These are our two assumptions. So now from Vieta's formulas, what we find, first of all, here if you apply Vieta's relation, the product of the roots z1, z2, z3 minus plus minus is minus c. So we get mod of z1, z2, z3 is equal to mod c, right? And we know that mod of Z1, mod of Z2 and mod of Z3 is equal to 1 given in the problem. So that implies that mod C equals 1. That is the first thing that we are getting, right? Now, what is mod of A? We know that Z1 plus Z2 plus Z3 by Vieta's relation is minus A. So mod of A is equal to mod of Z1 plus Z2 plus Z3, and therefore it must be less than equal to mod of Z1 plus mod of Z2 plus mod of Z3 by triangle inequality, which is equal to 3. So we are getting mod of A is less than equal to 3. So far we have gotten mod C is 1, mod A is less than equal to 3. Now let's look at the mod B term also. We'll do it on the next screen. By Vieta's relations again, Z1 Z2 plus Z2 Z3 plus Z3 Z1 in the equation is equal to plus B. So that implies that mod of Z1 Z2 plus mod of Z2 Z3 plus mod of Z3 Z1 is equal to mod of B. Now here we can do a simple operation. We can take mod of Z1 Z2 Z3 common. You are ending up with 1 by Z1 plus 1 by Z2 plus 1 by Z3, which can be written as this mod of Z1 Z2 Z3 is actually simply 1, and 1 by Z1 Z2 Z 1 by Z1 plus 1 by Z2 plus 1 by Z3 can be written as mod Z1 square by Z1 plus mod Z2 square by Z plus mod Z3 square by Z3, which is equal to Z1 conjugate plus Z2 conjugate plus Z3 conjugate, right? Now we are getting this condition here. So this is equal to mod B, which means mod of Z1 plus Z2 plus Z3 whole conjugate is mod B, right? Now we know that the conjugate is unchanged. The modulus of a conjugate, we know that Z modulus is equal to Z conjugate modulus, right? So this modulus will be same as Z1 plus Z2 plus Z3 modulus, which is equal to mod A. So we are getting mod A is equal to mod B. So far what we have gotten is that mod C is 1, mod A is less than equal to 3, and we have gotten mod A is equal to mod B. These are the results that we get by applying absolute values and Vieta's relations in equation 1, right? Now let's turn our attention to equation 2. The equation 2 was this, right? And this equation, applying the fact that mod A and mod B are same and mod C is 1, we can write it like this: x cube plus mod A x square plus mod A x plus 1. And this part, we can actually factorize this minus 1. If you put x is equal to minus 1, you get minus 1 plus 1 minus 1, which cancels, and plus 1. Yeah. So minus 1 is a factor, so you can take x plus 1 common, and by dividing you should be able to obtain the other factor. So you can easily prove that x cube plus mod A x square plus mod A x plus 1 is equal to x plus 1 times x square plus mod A minus 1 x plus 1. This is obtained by dividing because we know x plus 1 is a factor, right? So for this polynomial, we already know minus 1 is a root, right? Minus 1 is already a root. And now we have to look at the roots of the quadratic equation here, right, to find the other roots. So let's look at the discriminant of this quadratic. Discriminant here would be mod A minus 1 whole square minus 4, right? So this can be factorized as mod A plus 1 and mod A minus 3. This is the discriminant. Now we know that mod A is less than equal to 3. In that case, if mod A is less than equal to 3, you have two cases. Mod A is less than equal to 3 then this part is definitely negative, and mod A plus 1 will be positive. So the overall discriminant is actually negative, because this part is negative and this part will be positive, because mod A will be greater than 0, but it is less than 3, right? Correct. So if this discriminant is negative, that means the quadratic here has two non-real roots. It has two non-real roots which will be conjugates of each other because all the coefficients are real, right? The two non-real roots will be complex conjugates of each other. So we'll call them, let's say R3 is equal to R2 conjugate. These are the two roots. So obviously, when we do product of the roots, we will have R3 times R2 conjugate. So basically what I'm saying is that the roots are R2 and R3, R2 and R3, where R3 itself is R2 conjugate, right? So the product of the roots will be what? Product of the roots will be R2 modulus whole square. Basically R2 times R2 conjugate. The product of roots is coming out to be 1. So what we get from here is mod R2 will be 1, right? So that will be equal to mod R3 also, because mod R3 is conjugate of R2. So mod R2 is equal to mod R3 is equal to 1. And if the discriminant, this was the case when the discriminant was negative, the discriminant could be 0 also. If the discriminant is 0, then that means mod A is equal to 3. And in that case, we have repeated roots. And basically, if discriminant is 0, we have mod A is 3 and repeated roots x squared plus 2x plus 1. And you'll get x plus 1 whole square here, right? So in that case, the whole thing becomes, this is a double root at -1. You already have a -1 root. So all roots are -1 in that case. All roots are -1 if the discriminant is 0. And if the discriminant was negative, I got the complex roots of it have modulus 1. Right? The real root of it also is -1, so it has modulus 1. So in all cases, we are getting the three roots of this are having modulus of 1. In both the cases, whether the discriminant is 0 or whether the discriminant is negative. Right? In every case, we are getting this. Okay. Let's look at a third problem, which will highlight the technique that we have learned in this video. This question says, given that A1 to A101 are non-zero real numbers, such that any of the polynomials ai1 x bar 100 plus ai2 x bar 99 and so on till ai101 has an integer root. Where, what is the meaning of this ai1 and all? ai1, ai2 till ai101 is a permutation of the numbers 1 to 101. Permutation of the numbers 1 to 101. So basically, it's a different arrangement of the numbers. I1, I2, it could be numbers like 2, 3, 98, 101, and so on. Some random permutation of the numbers. So basically, you're saying this first coefficient could be A2, could be A101, could be any permutation, right? So you can make so many different polynomials out of this, right? You'll have 101 numbers, there are 101 factorial permutations. So there will be 101 factorial different polynomials. The question's claim is basically saying that given these 101 numbers, such that any permutation, if you put the coefficients in any permutation, this polynomial has an integer root, right? We have to find, now the question is asking us, find all possible values of a1 plus a2 plus a100. Find all possible values of the sum of these coefficients. Correct. So what we will try to do here is that we know that all of these polynomials have an integer root, right? We will show that at least one of these polynomials, at least one of these polynomials, at least one of these polynomials has 1 as a root. What is the benefit of this? If 1 is a root, if that is true, if 1 is a root, then a1 plus a2 plus a101 will be equal to 0 because p of 1 is 0, right? So we will get 0 as a possible value of a1 plus a2 till a101. So this is the first thing that we are trying out. So let's see what happens. So without loss of generality, we can assume that a101 is the maximum coefficient, or it has the maximum modulus, is equal to max of basically a1, a2 till a101. This is just an assumption right now. So now we will consider a particular polynomial. Consider the polynomial a101 x power 101 plus ai1 x power 99. Okay, actually this was power 100. The first term was power 100 plus ai2 x power 98. Finally ai100. Here I1, I2 till I100 is a random permutation, of the numbers from 1 to 100. We are saying right now that A101 is the term with the maximum absolute value, and after that we have a random arrangement of the remaining numbers, and this is the polynomial that we are considering, right? Now if mod r is greater than equal to 2 is a root, if mod r is greater than equal to is 2 is a root of this polynomial, then obviously what we can say is that a101 r power 100 is equal to minus ai1 r power 99 minus ai2 r power 98 and so on minus ai100, right? This is the standard technique that we saw in the beginning of the lecture, right? So what we can say here is a101 will be equal to minus ai1 by r minus ai2 by r square and so on minus ai100 by r power 100, right? This is the result we are getting. We have made the assumption that mod r is greater than equal to 2 is a root of this polynomial, right? Let's see what we can do from here. We'll apply absolute value on both sides. We get a101 is equal to mod of negative ai1 by r so on ai100 by I power 100 and apply triangle inequality. So this is less than equal to mod of ai1 by r plus mod of ai100 by r power 100 And obviously, we have assumed that A101 is the maximum absolute value. So if I replace all of these coefficients with A101, that is going to be larger. We can say that this is less than equal to mod of A101 common 1 by mod r plus 1 by mod r square till 1 by mod r power 100. I have just replaced each coefficient with a larger term. This is larger. We had assumed that in the beginning, right? So now what we can say here is that mod r is greater than 2 is my assumption, greater than equal to 2. So I can replace all of these with the lower value of 2 and the fraction will be bigger because otherwise mod r is bigger than 2, so it will be smaller. Right? So I can say less than equal to mod of A101 1 by 2 plus 1 by 4 till 1 by 2 power 100, right? Basically, the value of this is less than mod of A101 1 by 2 plus 1 by 4 plus infinity, right? Instead of a finite series, I have replaced with a bigger infinite series. The sum of the infinite series is 1 by 1 minus half. So that is equal to twice, right? No, it is half by 1 minus half. You see, the first term is half, common ratio is half. So it is equal to 1. So we are getting mod of A101 is less than equal to this, but that quantity is less than 1, mod of A101, which is a contradiction, right? So this is a clear contradiction. Mod of A101 cannot be less than mod of A1, right? So that means our assumption that the roots R is a root greater than equal to modulus of 2, modulus of R is greater than 2 is incorrect, right? So our root must have mod R is less than 2, right? We also cannot have a root at 0 since all the AIs are non-zero. The question had said that A1 to A101 are all non-zero. So any polynomial using these coefficients cannot have 0 as a root. Because if you put 0, at least one of the terms is the constant term. So 0 cannot be a root for this. So if 0 cannot be a root and mod r is less than 2 and there must be an integer root, then the integer root can only be mod r is equal to 1, right? Or basically r can be plus or minus 1, right? Correct. So what we have concluded by the contradiction is that mod r must be less than 2. And since it's an integer root and 0 cannot be a root, the only options are now left for us are minus 1 and 1, right? So if we can somehow show that minus 1 is not allowed, r is equal to minus 1 does not work, then we will be left with r is equal to 1, right? Correct. So what we need to show that minus 1 cannot always be a root for all of these polynomials. Cannot always be a root for all these polynomials. This is the point that we need to prove now, right? So let's see how we prove that. Let's look at two given polynomials, two random arrangements of the terms, a101 x power 100 plus a100 x power 99 and so on till a2x plus a1. This is one polynomial. And another polynomial is a101 x power 100. This time I will switch the coefficients of this. I will say a1 x power 99 and I will go on to a99x and a100 comes here. I have basically flipped the coefficients of all of these terms. Let's look at these two polynomials, right? Now, if r is equal to minus 1 is a root of both of them, both, right? Because what we have said is that for all the polynomials, there is at least one integer root. So they must have one common integer root. So if r is equal to -1 is that root, then what we will get here is from here we will get from the first one we get a101 minus a100 plus a99 minus a2 plus a1 is 0, and from the second one we get a101 minus a1 plus a2 plus a99 minus a100 is equal to 0, right? Like if you add both of them, what you get from here, adding both of them, you get a101 is 0, which is contrary to our hypothesis that all the AIs are non-zero. All the AIs are supposed to be non-zero, and we have just proven by a counter example that if -1 is a root for both the polynomials, we get a101 as 0, right? Which means that -1 cannot be, r cannot be -1, so r must be 1. 1 is the root, that is a common root for all of these polynomials. But there must be at least one polynomial with 1 as a root. So if there is at least one polynomial with 1 as a root, you get a1 plus a2 till a101 is equal to 0. So this 0 becomes our answer. So that is the solution. The question was looking at all of the possible polynomials. We had to show that any of these polynomials has an integer root. Some polynomial out of those has an integer root, where I1 to I101 was a permutation of the coefficients. What we showed was mod r cannot be greater than 2 for any such polynomial. So mod r must be less than 2. We got that by a contradiction using the triangle inequality technique that we have developed. And after that, what we got was basically that if mod r is less than 2, 0 cannot be a root of any of these polynomials, and -1 also cannot be a root of any of these polynomials, right? Right. So that concludes our proof here. And next thing that I wanted to point out for you is an interesting lemma. This is a very important theorem that you should be aware of. I will just state it. The proof can be done, but I will leave that to you. Uh, if the coefficients, if the coefficients of p of x are positive real numbers in ascending order, then all the roots of p of x, all roots of p of x lie outside or on the unit circle, or on the unit circle. What is this saying? If the coefficients of p of x are positive real numbers in ascending order, then all the roots will be outside the unit circle or on the unit circle. And the corollary to this is, if the coefficients of q of x are positive real numbers in descending order, then all the roots lie inside. Then all the roots of q of x lie inside or on the unit circle. This is a very important result in Olympiad problems. The proof of it can be done by the same absolute value method. So I would invite you to take a polynomial with ascending order of coefficients. Try to show that the roots lie outside the unit circle. Can be done by the same complex triangle inequality method that we have developed. So keep this theorem in mind. This will be handy for you while solving Olympiad problems. That's about it for this lesson. We will continue in the next class with more problems and more techniques. So I'll see you next time.